So now we will define some of the important interaction as I already discussed. Like in thermodynamics, we are having two kinds of energy interaction like work transfer and heat transfer. So I will define the energy interaction. So energy interaction between system and surrounding. System and surrounding. First, I am defining the heat transfer. So we can define the heat transfer. It's an energy interaction between system and surrounding due to temperature difference. So we can say that energy interaction between system and surrounding means system and surrounding due to temperature difference. So the energy interaction between system and surrounding due to temperature difference is called heat transfer. Similarly, I can define work transfer. So work transfer, it is energy interaction between system and surrounding other than heat transfer. Energy interaction between system and surrounding other than heat transfer. Or I can define in other words energy interaction between system and surrounding due to other than temperature difference is called work transfer. So both heat and work depends on the path. So I can write heat and work both depends on path of process. So they are called path function. Path function. So heat and work both depends on path of the process. They are called path function. They are not properties of the system. So heat and work, these are not properties of the system. It's a very important point. So remember this thing. Heat and work are not properties of system. These are boundary phenomena. Because whenever the energy interaction will takes place at boundary of system and surrounding, then only we are defining heat and work, and this heat and work are depends on the path of the process. These are not called path function. So I will define one more terminology, that is point function. Point function will depend on initial and final position of the system. Path function depends on initial and final state of system. State of system. They do not depend upon path of the process. So the point function depends on initial and final state of system. So we can say that properties are point function. Point function. So properties are point function. So remember what is the meaning of path function? What is the meaning of point function? And on which thing path and point function will depend. Now, one important thing in thermodynamics, that is cycle. In cycle, it's a combination. It's a combination of process such that initial and final state of system remain same. So cycle, it's nothing but a combination of process such that initial and final state of the system remains same. So I am just drawing a arbitrary cycle to dummy cycle on PV diagram. So here say 1 point. So 1 to 2 there is one process. 2 to 3, 2 to 1 again there is a one process. So it's called cycle because we are starting from 1, we goes up to 2 by process 1, and from 2 to 1 again we come back to 1 by process 2. So in this thing the system again come to 1 from 1 to 2 or 2 to 1. So the initial and final state of the system will remain same. In this example it's 1. So we can say that the system is following a cycle. So now we will start with various kinds of thermodynamics laws. So we will start with zeroth law of thermodynamics. Zeroth law of thermodynamics. So the temperature measurement is based on zeroth law of thermodynamics. So we can say that basic of temperature measurement. Temperature measurement. So the zeroth law of thermodynamics is nothing but basic of temperature measurement. So let's talk about three kinds of system. Suppose a system A, system B, and system C. So according to the zeroth law of thermodynamics, if system A and C are in thermal equilibrium, and if B and C are also in thermal equilibrium, then A and B will be in thermal equilibrium. So I will again repeat what is the zeroth law of thermodynamics. If A and C are in thermal equilibrium, I am not talking about thermodynamic equilibrium. I am just talking about thermal equilibrium. If A and C are in thermal equilibrium, and if B and C are in thermal equilibrium, then definitely A and B will be in thermal equilibrium with each other. So again I am writing here the zeroth law of thermodynamics. If A and C are in thermal equilibrium, are in thermal equilibrium, and B and C are in thermal equilibrium, are in thermal equilibrium, then A and B will be in thermal equilibrium. Thermal equilibrium. So this is regarding zeroth law of thermodynamics, which is nothing but the basic of temperature measurement. Now I will talk about first law of thermodynamics. First law of thermodynamics. So first law of thermodynamics, it's nothing but law of conservation of energy. It is law of conservation of energy, and according to this law, energy cannot be created nor be destroyed, but it can change from one form to another form. So I will again repeat the first law of thermodynamics. It is nothing but law of conservation of energy, and according to this law, energy cannot be created nor be destroyed, but it can change from one form to another form. So now I will define first law of thermodynamics for non-flow process and for flow process. So let's talk about first law of thermodynamics for non-flow process, non-flow process, or we can say that for closed system, because basically we are interested in two kinds of system, for closed system and open system. So first we will apply the first law of thermodynamics for closed system. If the system is closed, then fluid will not enter or fluid will not out. Means there will be no flow. So that's why I am calling for non-flow process. So now let's take a closed system. Here I am taking a closed system. Here I am giving a heat, suppose del Q. And if I am giving a heat, so according to first law of thermodynamics, whatever energy we are giving, it will change from one form to another. So we are giving heat here. So this heat can either be useful in doing work, or it can increase the internal energy of the system. Internal energy, that is generally defined by U. So in terms of del Q, I am writing del Q, so it will be del W and it will be del U. That is changing internal energy. So for closed system, I can write, if I am supplying heat, so it can increase or decrease the internal energy, that is change in internal energy, plus system can undergo some work, that is del W. So it's a law of conservation of energy, means I am giving some energy here and it can convert into this form. So it's nothing but law of conservation of energy. So we know, we have already discussed about Q, that is heat. We have already discussed about W, but there is one more term, that is internal energy. So I am defining internal energy first. Internal energy. So internal energy, it's the energy of atoms or molecules of a substance, including kinetic energy, vibrational energy, rotational energy, chemical energy, magnetic energy, nuclear energy, etc. So internal energy, it's the energy of atoms or molecules of a substance that includes various kinds of energy, maybe kinetic energy, vibrational energy, rotational energy, chemical energy, or magnetic energy, nuclear energy, or we can say that all kind of energy at a microscopic level. So now I am using the term microscopic. So now I would like to define what is the meaning of microscopic and macroscopic. So let's start with microscopic view. Microscopic. Microscopic view. So if we are looking the activity at the molecular level, that is called microscopic view. If we look activity at molecular level, then it's called microscopic view. Similarly, I can define macroscopic view. If we look activity on certain quantity of substance, then it's called macroscopic view. That is the basically difference between microscopic view and macroscopic view. So for internal energy that is generally defined by U, it's combination of all energy of molecules at microscopic level. So internal energy is nothing but a combination of all energy of molecules at microscopic level. So I will again rewrite the first law of thermodynamics for non-flow process. So first law of thermodynamics for non-flow process. So I am writing like del Q equals to del U plus del del. So here I am neglecting the kinetic and potential energy. So I am neglecting kinetic energy and potential energy of system. I am just considering the internal energy. So now we can define one more term, that is complete energy. So it will be internal energy plus kinetic energy plus potential energy. So we can define this the letter E. So now I can again rewrite the first law of thermodynamics for non-flow process with consideration of kinetic energy and potential energy of system. So now my first law of thermodynamics will be del Q equals to del E. In place of del U, I will write del E because I am also considering kinetic energy and potential energy of the system. So this one is the first law of thermodynamics for non-flow process with consideration of kinetic and potential. Suppose I am considering only displacement work. Here, displacement work I will define displacement work. It is nothing but dW equals to PD. So for displacement work alone, I can rewrite the first law of thermodynamics, del Q equals to del E plus PD. So this one is the first law of thermodynamics for non-flow process where we are considering kinetic and potential energy. That's why we are considering total energy, and here we are considering only displacement work. In the previous equation, we are considering all kind of work. So we can write this equation like for reversible process, for reversible process. So now I have to define what is the meaning of reversible process. Means in reversible process, if we can achieve the um, previous state, or we can achieve the initial state without changing anything in system and surrounding, that is called reversible process. And in irreversible process, we can't achieve the initial state of the system without disturbing system and surrounding, that is called irreversible process. So for reversible process, we have one term, later we will go into detail, but right now I am writing for reversible process I can write del Q equals to TdS. So for first law of thermodynamics for non-flow reversible process I can write TdS equals to del E plus ED. That is the first law of thermodynamics for non-flow reversible process, because I am using TdS. TdS I am using only for reversible process. Here we are considering the total energy that includes kinetic energy, potential energy of the system as well as internal energy, and here I am considering only displacement work. So these are the uh, um, various kinds of way how we can write the first law of thermodynamics depending on which kind of process, which kind of energy we are considering, which kind of work we are considering. So by this way, easily we can define the first law of thermodynamics for different processes. Now for first law of thermodynamics we have some sign convention. So I will discuss about the sign conventions. So work done work done by system, then we can say it's positive. Work done on system, that is negative. Similarly, heat supplied to system, it's positive. Heat lost by system, it's negative. So these are some of the sign convention we have to use when we are applying the first law of thermodynamics. So before defining the first law of thermodynamics for flow process, let's understand what is flow work. So flow work, we can define it's a product of pressure and volume. That is specific flow work. We can say that it's a specific flow work. Flow work, because we are defining flow work per unit mass. If we are considering mass, then it will be in terms of considering a small mass, so we can say PV, we can say. That is the flow work. So understand this specific flow work we can define for PV, and for if we are considering the mass, then flow work will be PVA. It's just a difference between specific flow work and flow work. Now we can easily define the first law of thermodynamics for flow process. Let's start first law of thermodynamics for flow process. So now I am considering one system here, and here suppose mass flow rate is m1 for one fluid, and here we are having this thing m2 dot, that is the mass flow rate at inlet and outlet. Suppose this one is inlet, outlet. Here velocity of fluid we can say v1. Here velocity of fluid we can say v2. Similarly, here the from bottom if we see, or in terms of potential energy, here we are having m1 g h1. Here potential energy we are having m2 g h2. So now if we apply the first law of thermodynamics, so here suppose the heat flow rate we are defining, that is q dot here, and work output suppose that is w. So now we can apply the first law of thermodynamics here. Here according to first law of thermodynamics, at section 1, or we can say that it's a section 1, suppose 1. So section 2, at 1 we are supplying q dot. The fluid is having energy v1, so the kinetic energy, and we are talking about in terms of rate, so 1 by 2 m1 dot v1 square. Similarly, we are talking in terms of per unit time, that's why I am using m1 dot, not m. If I am not talking with respect to the time, then directly we can use the kinetic energy, that is 1 by 2 m v square. So it's just for representation. Then I can write m1 dot g h1. Now here the fluid is entering into the system, means we are doing some work on the system, and according to the first law of thermodynamics, if we are doing some work on the system, it is negative. So the flow work we are doing here for entering the fluid into the system, so flow work we know it is nothing but P1 V1 M1 dot, and it's negative because we are doing work on the system. Similarly, for other side, we are having the work W that is done by the system. Now we are having the kinetic energy 1 by 2 per unit time, that is 1 by 2 m2 dot v2 square, plus potential energy per unit time m2 dot g h1, and here the fluid is flowing out of the system, means work done by the system, so it will be positive, so plus sign for this flow work P1 V1 M2 dot, sorry, it may be P2 V2, and here it is H2 because we are taking these things at 2. So now if you see this, we are having this term, and one more term we are forgetting here. We are considering heat, we are considering kinetic, potential, and over, but we have to consider also which energy? Internal energy. So the internal energy here will be U1. So for this thing it will be M1 dot U1. Similarly here we are having M2 dot U. So if we are talking in terms of per unit mass basis and without considering the with respect to the time, so I can write Q plus V1 square by 2 plus GH1 minus P1 V1 plus U. This based on per unit time with considering mass. Okay, it's based on this equation based on per unit time. Okay, and this equation based on per unit mass. And here I am considering here, it is on per unit mass basis here. Similarly, for per unit mass basis here I can write W plus square plus GH2 plus P2V2 plus U2. One more thing, I am again uh, specify this thing here. Now for this equation I am using steady flow energy equation. Steady flow energy equation. Steady flow energy equation means the characteristics of the flow will not change with respect to the time. Suppose here we can say that m1 dot equals to m2 dot for this thing. If we apply the steady flow energy equation, that's why I am balancing this. If I can write either m1 dot or m2 dot. So if you see, there will be no mismatch with respect to the per unit mass, because whatever the per unit mass I am using for LHS, the same per unit mass I will use for RHS. But we have to specify, we are writing the equation for steady flow energy equation, where the characteristics, like characteristics means properties, will not change with respect to the time. So now we can again rewrite this thing. Now I can again rewrite this thing. Q plus V1 square by 2 plus GH1 minus P1 V1 plus U1 W plus V2 square by 2 plus GH2 plus P2 V2 plus U. So here actually one more thing here, I am considering this flow work, right? If I suppose I will consider the net work, that is W, and it should be like P2 V2 because the system is doing work on flow, and P1 V1 because um, the work is done by the fluid on the system. So if I take this thing, then we can take minus sign here. But for equating the energy, the right thing is that we have to use plus sign here for that. So actually it's just a representation. If suppose I am talking energy at one section, so directly you can add as a flow energy. Similarly, at the second section also you can use the flow energy, right? So if we are writing in terms of W net, then only you can consider the sign. Okay, so by mistake we took the negative sign, but if we write the W net equals to W, then we have to see the sign, it's a negative or it's a positive. So I am correcting here, you can just take the positive because we are taking energy at section 1 and energy at section 2. So I can just write one more thing here for understanding. Energy at section 1. Similarly here I can write energy at section 2. energy at section 2. So now, with the help of per unit mass and for steady flow energy equation, I will again write this thing. But one more thing I will define, that is enthalpy. Enthalpy. Enthalpy is denoted by H, and it is nothing but the summation of internal energy and product of pressure and volume. So this one is the enthalpy here. So in place of P1V1 plus U1, I can write H1. Similarly, in place of P2V2 plus U2, I can write H2. So now if I again rewrite the above equation, this equation, then I can write Q plus P1 square by 2 plus GH1 plus H1. I am introducing H1 in place of P1V1 plus U1. Similarly, W plus U2 square by 2 plus GH2, and I can write H2. So here I am considering kinetic energy, I am considering potential energy. So this is the steady energy flow equation. So I can write it's a steady energy flow equation. It's a steady energy flow equation for flow process, including kinetic energy and potential energy of system. Suppose I am neglecting this thing, then Q plus H1 equals to W plus H2. So Q equals to H2 minus H1 plus W. So Q equals to LH plus W, or in other words, del Q equals to LH plus del W. So first law of thermodynamics for flow process, neglecting kinetic energy and potential energy. Now we can also write the first law of thermodynamics for flow process, non-flow process. So it maybe we can easily understand what is the difference if we go from non-flow to flow. So del Q equals to del U plus del W. So I am writing here first law of thermodynamics, for non-flow process, neglecting kinetic energy and potential energy. So now if we compare for non-flow process, neglecting kinetic energy and potential energy, we are taking the difference of internal energy. But if we are considering first law of thermodynamics for flow process, neglecting kinetic energy and potential energy, we are taking the difference of enthalpy. That is the only one difference if we go from non-flow to flow. And why this difference is coming? In case of non-flow, we are having only internal energy, and in case of flow process, we are having enthalpy, because we are having some flow work is there in case of flow process, that is PV. So this PV will add into U, it will give enthalpy. So that's why in flow